Okay, so look familiar? This was kind of a figure that I brought in from your textbook kind of quickly to show you so you guys could do those last two problems that were assigned for today. So when they talk about collecting a gas over water, basically you have the collection vessel, and the reason I want to emphasize this is tomorrow's lab, actually you're going to be doing this sort of technique. And you'll get lab credit for filling out a lab worksheet with your data before you leave. So then what you do is you bubble the gas of interest into the inverted gas collecting container that's over water. It doesn't work for all reactions, but it works for a few. So the thing is like I said on Monday, and what your textbook says, is not only will you have that gas of interest, but you'll also have water vapor, H2O gas there. And that's the one thing I want to take just a minute to look at. How does that water vapor hang out? And you saw that table that basically you'll have a different amount of water vapor at different temperatures. Okay, so we're kind of building up to that. So that actually, the amount of water vapor at different temperatures is going back to something called equilibrium vapor pressure. And actually in the second semester of this course, we kind of start out talking about intermolecular forces and liquids that tend to go into their gaseous state and form a vapor, like water. It's not real volatile, but other volatile liquids are even more better at creating these equilibrium vapor pressures. Okay, so one of the things I think is so cool, and you guys intuitively would know it, is when we talk about this process of a liquid going to a vapor and a vapor going back to a liquid, I think of this whole, there's my famous beaker, right? There's liquid down here. It could be water, or it could be something like ethanol or acetone, something that's even more susceptible to going into its vapor phase. We go ahead, and it looks kind of loose, but I'll put a watch glass over the top, so I'm containing the gas of interest is right there in that headspace above the liquid. So the cool thing is when we talk about the dynamic process, basically you have liquid going to form a gas, of course we call that evaporation, and gas going back to form a liquid, we call that condensation. So it's a back and forth, back and forth, back and forth. And the thing is, if you let a certain amount of time elapse for this system, I know it's a fancy system with a liquid that has a headspace of space and over it where the liquid could go back and forth between its vapor phase and it's sealed. You give it time and you're going to reach a certain amount of saturation. We talk about that actually in meteorology. But your space above your liquid becomes saturated with that particular, with vapor of that particular liquid. Okay, so what I just kind of said, kind of given time, is what you're just going to see from left to right. So the little red things are what? Evaporation, liquid going to a gas. Okay, here, given a certain amount of time from left to right, now you have some condensation. Okay, those little gray particles are gas particles that are going to go ahead and saturate the space above the liquid. Okay, at some time t, you actually have this space saturated with that species of interest. That's to say that basically, have you ever heard that the air can only hold so much water vapor? That's kind of what we're talking about. That air, that space above that liquid can only hold so much of that material in its vapor form at that particular temperature. It's an equilibrium vapor pressure. So just a few more. Here's some of my favorites. If you figure atmospheric pressure is about 760 millimeters of mercury, these are way below atmospheric pressure. But again, if you kind of picture the liquid with a liquid in a water in a beaker, and you cover the beaker and let time elapse, these are the saturation amounts of water that will be in the vapor form in that headspace in terms of pressure. Okay, smaller table, same information. So in tomorrow's lab, we're definitely going to get a fix on what the temperature of the room is, and then you'll look on a table to get the partial pressure of water. right. So like I've been saying, the amount of water that will be in equilibrium is dependent upon the temperature. All right, so let's work a problem, and we'll call it that. Actually, I went ahead and worked the same problem on, or kind of set it up on a little page of its own here in a minute. But take your time when you're given a problem like this. Kind of get your wits about you. Notice that they don't give you the mass of the potassium chlorate that you're decomposing into potassium chloride and oxygen. Okay, so let me go ahead. You guys already have that, and I will show you kind of, oops, that is what I want to do. Come back. That's what I want to do. Okay, so this actually is diagramming that information that you already have in front of you. Okay, so the balance equation's given. Notice that you have a solid substance you're going to heat up. It's going to decompose. You're going to get a solid and a gas. With regard to the oxygen, it's going to be captured. They give you the volume. They give you the temperature. Notice they give you the total pressure. If you read the little paragraph that goes with the problem, that 764 millimeters of mercury is total pressure. You're like, what do you mean total pressure? Well, there's two pressures in that volume. There are two gases in that volume. There is your gas of interest, your O2, and there's also H2O. So the total pressure is the sum of the two pressures, partial pressures. So we can get when we work the problem here in a minute, we're going to look for 25 degrees Celsius, we're going to look at what the vapor pressure of water is, and we're actually going to plug that in here, and we can go ahead and do a subtraction and get the partial pressure of O2. So then the two problems you're supposed to work, one is what will be the mass of the O2 collected over there? Well, you can get to moles once you get the partial pressure of oxygen here by subtraction. Then you'll have three of your four variables of PV is equal to nRT. You can get to N, and then use the molar mass of oxygen to get to grams. And then the second part is what is the mass of KClO3 that was decomposed. And so we can go ahead and use these moles of O2, use stoichiometry, the whole 2 moles to 3 moles, stoichiometry to get the moles of KClO3. Then we can use the molar mass of KClO3 to get to the mass of KClO3. So that's basically what we're going to do. Okay. So the next page on your little sheet looks something like this. Okay, the total pressure that's being confined over there after the reaction is equal to the partial pressure of the gas of interest plus the partial pressure of water, because it was collected over water. From the table, the partial pressure of water at 25 degrees Celsius is 24 millimeters of mercury. And then go ahead and do the subtraction. So the 764 minus 24 is equal to 740 millimeters of mercury. So that's your partial pressure of O2. You guys are doing pretty good working your gas law problems, kind of diagramming what you're after and what you know. So that's what we're going to plug into PV is equal to nRT to get to the moles of O2. So moles of O2 coming up. First we need to fix the temperature from Celsius to Kelvin by adding 273 to 25. So 298 Kelvin is what we're looking at. Then we can go ahead and get the partial pressure of we need to fix the partial pressure of O2 from units of millimeters of mercury we had a minute ago to units of atmospheres by multiplying by 1 atmosphere over 760 millimeters of mercury. Now we're ready to plug in for N. Okay, so the number of moles of oxygen will be equal to the partial pressure of oxygen, 0.974 atmospheres times the volume, 0.250 liters, divided by the ideal gas law constant, 0.082058 liters atmospheres per mole Kelvin. Also in the denominator is the temperature in Kelvin, 298 Kelvin. Rounding to your You're doing good other ways, but rounding to 3 sig figs, okay, 0.00998 moles of O2. And we're not quite done yet because they wanted it in grams. So we're going to have to take this moles times its molar mass. So the 0.00995 moles of O2 times 32.00 grams per 1 mole. So that's the answer to 1. 0.319 grams of O2.
The answer on the, it is 1.998.
Oh. Yeah, I don't know. I don't have a calculator with me. Good catch, though. I don't know if you guys see what she's saying. She says this on the next one says 995. You plugging it in, Kelsey? No. We'll chase it down afterwards. How's that? I agree, Heather. They should be the same number. So that is the answer to the first one, 0.319 grams. So the second part of the question was basically it's stoichiometry to get back to grams of the potassium chlorate that was decomposed. You'll need to know, and you have it written down, the molar mass of KClO3. Okay, so if we start with the moles, which we already know, plug in the stoichiometric ratio from the balanced equation. We know 2 moles of KClO3 will react for every 3 moles of O2, and then knock in this molar mass of KClO3. Then we should get to the grams of KClO3. Round to 3 sig figs, 0.813 grams. And that's it. If I'm going to fix that, I better do that before next fall, because I so would not catch that again. Or I wouldn't catch it. So. Does that work? So, like, there's no homework problems because you already handed them in. But we kind of talked about this. So, all right. One last thing to cover. So PV is equal to nRT is called the ideal gas law equation. But what if the gases are not behaving ideally? That's exactly what we're going to talk about, non-ideal gas behavior and kind of how PV and NT are related to each other then. Okay, so if somebody says the gas is behaving ideally, then it can follow PV is equal to nRT. Now, I'm going to show you an adjustment to the ideal gas law, and it's called van der Waals equation. There are no homework questions over van der Waals equation to address gases that are behaving badly, behaving non-ideally. There are no problems for you to do, but I just want you to know about it. Okay? All right. So, in general, and this kind of, I'm going to bring up the 2 assumptions. Remember we said if a gas is behaving ideally, then there were 2 assumptions. You're going to see it here in a minute. Again, that basically there is no interaction between gas particle, and the volume of the gas particle basically is 0 compared to the container it's in. And so actually those 2 assumptions work pretty well. The more a gas is more like a gas and less like a liquid. Okay, so the more it becomes closer to a liquid, you're like, oh, dang, I think it's going to behave badly. And you're right. And if you think of how do you get a gas to become a liquid, well, you cool it down. Another way you can get gas to become a liquid is to pressurize it. Okay, when you buy bottled gas, that's what they've done. Pressurized it. Made it to form those intermolecular bonds. So, temperature and pressure. I'm going to give you a look at something called the pressure-temperature curve. Okay, and guess what? It plots pressure and temperature for a given substance, and on a pressure-temperature curve, it also gives for that substance, will that substance be a solid, will it be a liquid, or will it be a gas on these curves? So we said that gas will be closer to an ideal gas if it's closer to a gas, I know it sounds dumb, but farther from a liquid. So if you heat it up a lot, okay, it's going to be ramming around, okay? So it's going to be high temperatures are preferred for a gas behaving ideally. Low pressures simply mean that basically for the given box, there's not many gas particles there. And to me, that works too, because they're not going to interact if there's not very many for a box. So gases will behave badly at lower temperatures, and if you have squished a lot in a box, which means high pressures. Low temperatures, high pressures, gas is not going to follow PV's equal nRT. Okay. So this is a temperature pressure curve for a particular substance. Now these pressure temperature curves take on kind of a Y sort of shape. Can you see the Y? Kind of looks like a wishbone. And we have temperature along the x-axis and pressure along the y-axis for the same substance. That kind of wishbone, that kind of Y, breaks the graph up into 3 segments. And those segments are if the substance is a solid, literally if it's solid, if that substance is a liquid, or if that substance is a gas. And intuitively, if you just think of kind of water going from a liquid to a gas or water going from a liquid to a solid, it kind of works for you. So, for instance, we could pick, let's see, this isn't water, so that's why it's not really going to work. But we could pick somewhere in here, kind of forget the pressure, and we could skip across and go from a solid, heat it up, go to liquid, heat it up, go to a gas. We could take a gas, cool it down, go to liquid, cool it down, go to a solid at a given pressure. Okay, that's all that is. And we'll talk more about those curves later. But for now, I just want to emphasize that this region right here, gases are behaving ideally. The farther from being a liquid, the better. What does that mean? High temperatures and actually lower pressures. Okay, so again, this is kind of the 2 assumptions we saw when we talked about PV equals nRT, or we talked about just general gas characteristics. So the 2 assumptions, the whole thou shalt not interact with other gas particles, and the whole thou shalt not have any volume. Well, at low at low temperatures, you're kind of going to have troubles not interacting with each other. Okay, that's to say that at low temperatures, the amount of kinetic energy the gas particles have is less and less, and they're like, okay, let's go ahead and play. Okay, so low temperatures are bad for ideal gases. And then the other thing, high pressures are bad for ideal gases. If your objective is to be an ideal gas, high pressures are bad. Why? Because in high pressures, basically, you have a lot of particles confined to a small space. And then the volume of the particles actually is significant relative to the volume that it's being contained in. You can't say it's 0 if they're all squished together. All right, so here we go. Van der Waals fixed PV equals nRT for non-ideal gas behavior. So here we go. See if you can find PV equals nRT there. Not too bad. Basically, and it says it on a slide coming up, your pressure term has something added to it. Your volume term has something subtracted to it from it. Is equal to nRT. Okay, so you know what PV and NT are. And A and B, you're going to see on the slide coming up, basically you have to look them up for the material of interest. The thing that you want to know how it's behaving, the gas, okay, you're going to look up the value for A and B. Those are the constants, okay? They're different for different gases, is my point. So it's just a little fixing on the P, a little fixing on the V, and you're good to go. Okay. So that first term corrects for pressure, like I said. That second term, the BN corrects for volume. And it's honestly kind of another one of those plug and chug things. That's the way I think of it anyway. So it's really not all that mysterious. I was looking at this at my desk and I'm like, now how does that work? Well, you figure the larger, can you guys see this? Because I bet you can. The larger the volume, if this becomes large, okay, the fact that it's in the denominator, the larger it is, basically that term goes to nothing. So if your volumes are large, you're like, hey, you can have low densities, low pressures, more ideal behavior. Okay. Similarly, over here, that's the number of moles of gas particles is being confined to a particular volume V. Okay. The smaller that is, okay, then the more wiggle room and the less interaction they have and the less significant the volume of the gas particle is relative to the volume of the container it's in. So you want to make volume large and you want to make N small. And it's just consistent with what we've been talking about. All right. So last slide, right? So this is just for some given substances. These are gases, or potentially gases, depending upon the pressure and the temperature. Recently, on my Facebook page again, I subscribed or follow some of these science Facebook sites, and it caught my attention because they said basically precipitation on other, and I don't know if it wasn't necessarily planets or stars, but depending upon the star or the planet's pressure and temperature, you can get other things to go through what we call a water cycle. Basically go from being a gas to a liquid, and once it's a liquid in the clouds, it can precipitate, it can evaporate, okay? Like Titan, which is an awesome moon around Saturn, it actually, instead of having water cycle, it has methane cycle, just because of the temperature and the pressure. So that's kind of a little bit more type of. Anyway, just to highlight one other thing, or is that right? Just highlight one other thing. We've talked a lot about dimensional analysis, which just makes sure that your units cancel. So I know it seems kind of strange, but it works because I've proven it to myself not that long ago. Basically, if you take these units and you plug them into there, and you go ahead and use units of N as moles, units of volume as liters, you square that term, you take it times that, and actually, can you see you're left with units of atmospheres. Similarly, over here, notice that in order to be correct, that B van der Waals constant needs to cancel out the moles that we're multiplying it by, so that's why it has units of moles in the denominator, and needs to be left with units of liters so it can work well with the volume term. So that all works. Okay, that's it. That's all I have.